S-Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Hello everyone. Can you tell me what's the common feature among these molecules that I have shown for you? Take some time, look through the molecules and tell me if you can tell me what is common between the following compounds. I'm Dr. Sujata Sengupta. Welcome to the S-Chan Academy. If you want to learn more about today's lesson, then please refer to the books by S-Chan Publishing, the link to which is provided in the drop box below. Alright, now let's come back to the question I'd asked you. What's the common feature in all of these molecules? If you've answered that they all contain at least one halogen atom, you're absolutely correct. All of these molecules are examples of organohalogen compounds or organohalo compounds, a class of organic compounds which will contain at least one halogen atom. What are the halogen atoms? Fluorine, chlorine, bromine and iodine. So in today's lessons, we are going to focus on the chemistry of these compounds which will contain at least one halogen atom. There are three major classes of our halogenated organic compounds: alkyl halides, vinyl halides and aryl halides. What are the difference between the three? Well, our alkyl halides will contain a halogen atom which is bonded to a carbon part of an alkyl group. Our vinyl halides will contain a halogen atom which is bonded to the carbon of an alkene, and our aryl halide has a halogen atom which is bonded to a carbon which is part of an aromatic ring. Now our vinyl halides and our aryl halides will show a distinct chemistry which is quite different from that of alkyl halides. Why? Yes, it is because due to the difference in the bonding and the hybridization of the carbon. In today's videos, we will be focused on the chemistry of alkyl halides, but please stay tuned and refer to our further videos on the chemistry of aryl halides. So now let's get started. Let's start with the nomenclature. So there are two distinct ways in which we can name our alkyl halides. The systematic or the Iupac nomenclature. It treats the alkyl halides as a haloalkane. So fluorine becomes fluoro, chlorine is chloro, bromine is bromo and iodine is iodo. And as a result, we come up with a systematic naming of the haloalkane. Certain alkyl halides have a common or a trivial name, where the name of the alkyl group comes before, followed by the name of the halide. For example, ethyl bromide or propyl chloride. And finally, some of the halomethanes have names which have no relation to their structure. For example, methylene halides or halophone or carbon tetrahalides. So, looking at this molecule here, according to the Iupac nomenclature, its systematic name is 1-chlorobutane, but it can also have a common or a trivial name of N-butyl chloride. Now, these alkyl halides can be classified according to the nature of the carbon atom which is bonded to our halogen. How does this happen? So, if the halogen bearing carbon is bonded to another carbon atom it is said to be primary, and the alkyl halide is a primary alkyl halide. If two carbon atoms are attached to the carbon bearing the halogen, then that carbon is said to be secondary, and the alkyl halide is a secondary alkyl halide. A tertiary alkyl halide will have 3 carbons which are bonded to the carbon bearing the halogen atom. If the halogen is bonded to a carbon which is a methyl group, then it is said to be a methyl halide. Finally, alkyl halides which contain 2 halogen atoms that are bonded to the same carbon, these are known as geminal dihalides. Geminal, you will remember, comes from the Latin word geminus, which means twins. And a vicinal dihalide has 2 halogen atoms which are on adjacent carbon atoms. Here, the word vicinal comes from the Latin word vicinus, which means neighbors. Perhaps the most important property of our alkyl halides is the fact that these molecules are polar in nature. Why is that? Let's look at their structure. If I write a typical carbon halogen bond, let's say CX, or let's look at a specific example, Cl. What do I notice in this carbon halogen bond? First of all, in our simple alkyl halides, the halogen atom is bonded to a carbon which is sp3 hybridized. The halogen atoms, if you notice, they are electronegative. What does this mean? It means that it draws the electrons in this carbon halogen bond more towards itself. What is the consequence of this? It means that this carbon halogen bond is going to be polarized, or we can say that it is a polar bond. Because the chlorine has a greater share of the electrons, it gets a slight negative charge, and our carbon is going to get a slight positive charge. This positive charge makes our carbon behave somewhat as an electrophilic molecule. Now, if we consider the different alkyl halides, and when we consider the different halogens, what do we notice? That the electronegativities of the halogens, it increases as we move from iodine to fluorine. But at the same time, the bond length between the carbon and the halogen, it increases as we go from carbon fluorine to carbon iodine. So these two effects, they oppose each other. What is the result? The result is that the bond dipole for these carbon halogen molecules, it increases in an order where the carbon iodide bond is going to be least polar or has the smallest dipole moment, and the carbon chlorine bond is going to be most polar. Now you may ask me, what is the consequence of this polar carbon halogen bond? Well, remember, most of the reactions of our alkyl halides will involve breaking of this carbon halogen bond. So, remember that our carbon halogens are going to be polar. So, what happens? Our carbon, which has a slight positive charge, it is somewhat electrophilic in nature, and therefore a nucleophile can come and attack this electrophilic carbon atom. The halogen can now leave with its bonded pair of electrons as a halide ion. remember, our halide ions are extremely good leaving groups. Why? Because they are weak bases. What is the consequence of the halide ions being good leaving group? Well, what can happen now is that, just as I mentioned, another nucleophile can come and attack our electrophilic carbon atom and the halide ion can leave. Such type of reactions are example of a substitution reaction, more specifically a nucleophilic substitution reaction. At the same time, what can also happen is that the halide ion can leave along with another atom, usually a proton. And when this happens, it results in the formation of a new pi bond. Such type of reactions, if you remember, are called elimination reactions. And the elimination of a halogen and a hydrogen is known as a dehydrohalogenation. If you have been following our videos, you will remember that these dehydrohalogenation reactions of alkyl halides are an excellent method to prepare alkenes and alkynes. If you don't remember, please do go back and watch our videos in the S. Chand Academy. Because alkyl halides can undergo both substitution reactions and elimination reactions, therefore they are excellent intermediates to the synthesis of a wide variety of functional groups or organic compounds. But you also have to remember that at many times these substitution and elimination reactions often compete with each other. So now let's go back and look at these substitution reactions of our alkyl halides. To do this, let's first consider the substitution reaction of iodomethane with the hydroxide ion. So here you can see I've written down iodomethane. This undergoes a nucleophilic substitution reaction with our hydroxide ion. Our hydroxide ion over here is our nucleophile, meaning that it is the source of our electrons. Iodomethane over here is our substrate, meaning it is the compound which is going to be attacked upon. All right? Our iodomethane contains a carbon iodine bond. What do we know so far? Because iodine is more electronegative, it is going to withdraw the electrons in the carbon iodine bond more towards itself. So what happens? It gets a slight negative charge and our carbon is going to get a slight positive charge. That is, our carbon is going to become electrophilic. So what happens now? Our nucleophile, the hydroxide ion, this is going to come in from the back. It attacks the electrophilic carbon but remember, carbon can only have 8 electrons in its valence shell. So this iodine is going to be lost in the form of an iodide minus. And so our product here is going to be methanol with the loss of I minus. So this, students, is an example of a nucleophilic substitution reaction. Let's learn or revise or recap this a little further. This type of a nucleophilic substitution reaction, which takes place in one step, is commonly known as an SN2 mechanism. The abbreviation stands for substitution nucleophilic bimolecular. What does this bimolecular mean? Bimolecular means that in the rate equation of the rate determining step, the rate of the reaction is dependent both on the concentration of our nucleophile and our substrate, the alkyl halide. These type of reactions are also concerted reactions. What does that mean? It means that it takes place in a single step where bond breaking and bond making takes place at the same time. Now, which factors are going to affect these SN2 mechanism? Well, first of all, the strength of the nucleophile. Obviously, stronger the nucleophile, the faster it is going to react compared to a weaker nucleophile under the same conditions. Number 2, better the leaving group, the faster is going to be our SN2 reactions. And that is why our alkyl halides, where the halogen leaves as a halide ion, are such good substrates for an SN2 mechanism. Next is steric effect. This SN2 mechanism, it works best for our methyl alkyl halides and for most primary alkyl halides. Secondary alkyl halides are a bit sluggish or slow in their reaction. And our tertiary alkyl halides, they do not react at all. And why is that? That is because of steric hindrance. The tertiary alkyl halides, remember, it contains 3 bulky alkyl groups. And due to the presence of these 3 alkyl groups, it is impossible for a nucleophile to come and approach and carry out the reaction. And finally, perhaps what is most important is if we have a chiral carbon which is undergoing this nucleophilic substitution, then a backside attack will result in the formation of a product which is going to have the opposite configuration. Such type of a displacement is known as a Walden's inversion. Let's take a look. So now let's consider the nucleophilic substitution of S2-bromobutane in sodium hydroxide. So this over here is my S2-bromobutane, and this undergoes our SN2 mechanism reaction with our nucleophile, the hydroxide ion. So again, we have the carbon-bromine bond where the carbon is going to be electrophilic in nature. Our nucleophile hydroxide attacks it from the backside, and what happens? Our bromine is going to leave as a Br minus. But let's draw the intermediate transition state. So here you notice so in our transition state, what is happening? The carbon Br bond is going to break, and at the same time our carbon oxygen bond is going to be formed. Alright, and now then what happens? We have a complete loss of the bromine as the bromide, and what do we get as our product? So you will notice here our product is going to be R2-butanol. So what has happened? There has been what we call as a Walden inversion, where there has been a change in the configuration. So this is another important characteristics of our SN2 reactions. Now, let's take a short break. But before we do, let me ask you a small question. Can you solve this reaction? Over here, you can see that tertiary butyl bromide is undergoing solvolysis in boiling methanol. Can you tell me what is the product? And do you think this reaction will also proceed via an SN2 mechanism? Try to work it out and we'll come back and I'll reveal the answer.
हाय, मैं हूं नेहा शर्मा और मैं आ रही हूं एस चांद अकेडमी में आपके फिजिकल केमिस्ट्री के डिफ़िकल्ट कंसेप्ट्स को इजी बनाने। सो प्लीज़ हमारे चैनल को सब्सक्राइब करिए ताकि आप अपनी सारी फिजिकल केमिस्ट्री की प्रॉब्लम्स को भूल जाएं और सबके सॉल्यूशंस आपको मिल जाएं।
So welcome back to the S. Chand Academy. Before the break, I left you with a question. So let's see if we can solve it together. I had asked you to consider the solvolysis of tertiary butyl bromide in boiling methanol. Were you able to find out what the product is? And does this follow an SN2 mechanism? So let's solve it together and see what it is. So I'm sure you have been able to guess the correct answer. Yes, a nucleophilic substitution of tertiary butyl bromide in boiling methanol leads to the formation of our methyl tertiary butyl ether. Now, first of all, why did I call this as a solvolysis reaction? Well, here methanol, not only is it the nucleophile, but it is also the solvent. So that's why it's also an example of a solvolysis reaction. So now the question is, does this reaction involve the SN2 mechanism? Here, what do you notice? You notice that methanol is our nucleophile. But is it a strong nucleophile? No, it's a weak nucleophile. Our substrate here is tertiary butyl bromide. It's a tertiary alkyl halide, which you know are substrates that do not undergo reaction by the SN2 mechanism. So what mechanism will be involved for this nucleophilic substitution reaction? The answer comes if we are able to study the kinetics of the reaction. What does that reveal? It reveals that in the rate determining step, the rate of the reaction is only dependent upon our alkyl halide, that is our tertiary butyl bromide. It does not depend on the presence of the nucleophile. Such type of reactions are known as an SN1 mechanism, or it stands for substitution nucleophilic unimolecular reactions. Here, unimolecular means that in the rate determinant step, the rate of the reaction is dependent only upon the concentration of our substrate. And when we look at the mechanism of the reaction, you will notice that the reaction takes place in steps with the formation of a carbocation. And that is why tertiary alkyl halides undergo reactions the best in this SN1 mechanism. So let's quickly look at how this reaction proceeds. Remember, I told you that this is a multi-step reaction. So in the first step, what happens is a slow ionization of our alkyl halide with the loss of the halide ion. So, I have my tertiary butyl bromide, and in the first step, there is a slow ionization with the loss of the halogen as the halide ion, and it leads to the formation of our stable tertiary carbocation. In the second step, this tertiary carbocation in a very fast reaction is attacked by our nucleophile. And finally, in the last step, the loss of the proton leads to the formation of our product, which is our methyl tertiary butyl ether. So, this was the mechanism of an SN1 reaction. So now, what can we conclude about our SN1 reactions? So here you have noticed it's a multi-step process through the formation of a carbocation. So factors which stabilize this intermediate carbocation will favor an SN1 mechanism. And that is why, like I've said before, our tertiary alkyl halides are so reactive by the SN1 mechanism. Resonance stabilization, whenever possible, for this carbocation will also favor an SN1 mechanism. The SN1 mechanism also works best in polar solvents. Why? Because they stabilize our carbocation. Many times you have noticed that our carbocations tend to undergo a structural change known as rearrangement. So, our SN1 reactions also sometimes will proceed with a rearrangement to generate the more stable carbocation. And finally, if you remember that an SN2 reaction proceeded with an Walden inversion, and they were stereospecific reactions. But in the SN1 mechanism, you will notice that our intermediate is going to be a planar achiral carbocation. And so our nucleophile can come in and attack from either face. We can have both retention and we can have inversion. So such type of reactions, they lead to what is known as a racemization. So these were the important characteristics of the SN1 mechanism. Now that we're clear with substitution, let's move on and look at a little more about the chemistry of our alkyl halides. There are a variety of ways or methods by which we can prepare our alkyl halides. Alkyl halides, they can be prepared through the free radical halogenation reactions on alkenes. But besides that, there are certain more interesting methods. For example, the treatment of hydrobromic acid with an alkene results in the formation of an alkyl bromide. So, such type of reactions are known as our addition reactions, and if you remember, they always proceed via the Markovnikov's selectivity, where the bromine atom will end up on the more substituted carbon atom. Similarly, if we take alkynes and we treat it with an excess or 2 moles of our alkyl halides, then that leads to the formation of a geminal dihalide. Addition of halogens to an alkene also results in the formation of our vicinal or our 1,2-dihaloalkanes. So, the halogens bromine and chlorine will add to the double bond of an alkene to form these vicinal dihalides. Now, if you remember this reaction, it proceeds with anti-stereochemistry through the formation of, for example, here a bromonium ion, and it always leads to the 2 bromines being added to the opposite faces of the double bond. This reaction, if you remember, is commonly done in our undergraduate organic chemistry laboratories. So, where the reaction involves bromine in solvents like carbon tetrachloride, and it is a standard test for the detection of the presence of a pi bond. So, for example, if a solution of bromine, which has a dark brown color, is added to an alkene, its color, for example, like cyclohexene, then the color gets discharged or it quickly disappears. Why? Because bromine has added to the double bond of cyclohexene. Finally, with the help of a variety of reagents, alcohols can also be converted into alkyl halides. What reagents can we use? We can use the corresponding hydrogen halides, we can use phosphorus tribromide, or we can also use thionine chloride. Now, what are some of the reactions which these alkyl halides can undergo? Like I've said, they are very important intermediates. They can take part in substitution and elimination reactions, and therefore they can lead to the formation of a variety of other functional groups. As we had discussed before, nucleophilic substitution using strong nucleophiles such as our hydroxides is an excellent way to prepare alcohols. Alkyl halides can also react with cyanide ion, and it gives alkyl cyanides which are known as nitriles. This also takes place via the nucleophilic substitution mechanism. Finally, dehydrohalogenation of the alkyl halide leads to the formation of an alkene. A strong base like potassium hydroxide is often used to carry out this reaction. Finally, we will end today's lecture with the Williamson's ether synthesis, one of the most reliable and versatile methods for the synthesis of organic compounds known as ethers. Ethers, if you remember, are those organic compounds with the general formula ROR, where the R can either be an alkyl group or an aryl group. You can think of ethers as being a water molecule where both the hydrogens are replaced with the alkyl or aryl groups. If the 2 R groups are similar, then they are known as our symmetrical ethers. If the 2 R groups are different, then they are unsymmetrical ethers. There are various ethers which are commonly used these days. One example is diethyl ether, which is an excellent solvent used in many organic transformations. So why are we suddenly talking about ethers? Well, because ethers are a common product of the nucleophilic substitution reaction. More specifically, the ethers are formed by an alkoxide attacking our alkyl halide. How do we get the alkoxides? Remember, the alkoxides are obtained when alcohols are deprotonated in the presence of strong bases like sodium or potassium metal. And this synthesis is commonly termed as the Williamson's ether synthesis, named after Alexander William, who first developed this reaction back in the 1850s. And till date, it is one of the best reactions for the synthesis of our ether molecules. We have in today's lessons gone over the chemistry of our alkyl halides. We have looked into details two of the most important reactions of the alkyl halides, the substitution SN1 versus SN2, and we looked at ways by which we can prepare alkyl halides and some of their important reactions. And don't forget the Williamson's ether synthesis for the preparation of ethers. I hope you liked watching our videos. Do follow the S. Chand Academy for our future videos. Don't forget to like, share, subscribe and hit the bell button. Thank you.